Hello and welcome to Stats. So what are we doing today? We are learning how to evaluate our regression equations. So I've said this before, but you can always calculate a regression equation, all right? It doesn't matter what the data looks like, what the data is about. Like, you can always run through the calculations and get an equation. But that doesn't mean that equation is actually useful. Remember, we're not just making these as like a intellectual exercise. They're usually helping us make decisions out in the real world. So if we're using these to make decisions out in the real world, we want some sense of how useful are they going to be? Are they going to help us make better decisions, or are we better off just flipping a coin? All right, so that's what we're going to look at today, is how do we evaluate these and see if we're doing a good job. All right, so if you look at this up here, it just says the point of a regression line is to help describe the pattern, right? Taking this cloud of points and mathematically representing it. At this point, we've talked about multiple ways to assess how strong the association is, primarily correlation. And then the form, we have to make sure that it's linear because correlation only applies to linear data. I mean, we saw before when we did that little exercise where we had 3 different scatter plots, they had totally different shapes, but they all had the same correlation. Correlation is only valid when you have linear data, all right? This would give us the same correlation as this, but this one is meaningless because the data is not linear, right? Correlation only has meaning when your data is linear, right? And that's what this bottom line is saying. By definition, correlation in the regression equation do not make sense unless the form of the data is linear. So if you're not dealing with linear data, it's all out the window, all right? Now, you can still run through the calculations, but the answers that you get are meaningless. And that's where you as the statistician have to recognize, like, okay, these are not the appropriate tools for this situation. Even if I can technically calculate it, it's not giving me a meaningful result. All right, now, what are we going to talk about today? We also, besides just looking at the scatter plot, need to check for patterns in the residuals. Any pattern suggests that the regression equation does not, all right, I'm going to emphasize that because a lot of times kids are like, oh, it's a pattern, that must be a good thing. When we're looking at residuals, patterns are bad things. All right, so any pattern suggests that the regression equation does not work well with the data. And what does not work well with the data mean? Generally, it means that it's not linear enough. Now, what's sort of the logic here? Well, if we go back and look at this graph right here, these are all below the line. So these right here would be negative residuals. All right. These are all above the line, so these would all give us positive residuals. And remember, the residual is basically the vertical distance down to the line. And then over here, these again would become, whoops, negative residuals. Right? So if we were to plot all of these residuals, which again is like the vertical distances to the lines, all right, we would see a pattern. There'd be a whole bunch of negative residuals on one side. There'd be a whole bunch of positive residuals in the middle. There'd be a whole bunch of negative residuals on the right side. All right, the fact that there's a pattern in the residuals is suggesting that the linear model is a bad fit, which in this case is pretty obvious because the pattern is curved, but in less obvious cases, the same logic applies. If we're seeing any sort of pattern in the residuals, it suggests that the linear model is not a good fit. In contrast, if we look at this one, here you've got a negative residual, here you've got positive, here you've got negative. This one's like a tiny positive. This one's like a tiny negative, positive. This one's like right on the line, positive, positive, negative, negative. There's no real pattern there, right? They're just kind of scattered about. Sometimes they're big, sometimes they're small, sometimes they're positive, sometimes they're negative. That's ideally what we're looking for, because then that suggests that you do have a linear model that's kind of appropriate for your data. All right, so let's talk about the residual plot, which we did kind of do half of a residual plot in the last notes, but I want to take a look at them in a little more detail here. So a scatter plot of the residuals against the explanatory variable which, just a reminder, is the x. All right, so it's a scatter plot of the residuals against the explanatory variable. Your y-axis is going to be your residuals. The x-axis is going to be your x variable. And it is used to assess how well a regression line fits the data. Okay. So it's kind of hard to see on the photocopy here, but basically on this one, we have a bunch of points that are scattered all around. Some have positive residuals, some have low residuals, some are close to the line, some are further away from the line, but there's no real pattern to what's happening there. All right, in contrast, here's one that's very clear. We've got a whole bunch of negative residuals, then we've got a whole bunch of positive residuals, then we have a whole bunch of negative residuals. And obviously this is a very obvious case, but this one is what we want to see. This is good. This is bad. All right, this suggests that our data is not linear enough because we're seeing some sort of pattern in the data. And again, this is about as obvious as it's going to get. And then just reminders, just want to make sure that we're clear on this, is the residual, again, is coming from y minus y hat. So just never hurts to give you that reminder. Now, let's take a look at this one, because this one's maybe less obvious what's happening. So if you take a quick glance at this, you're going to say like, oh, all right, this looks pretty good. They're scattered above and below. What's wrong with this one? All right. Well, what you can notice is that down at this end, the residuals are fairly small. And at this end, all the residuals are fairly large. So this can represent a pattern, all right? Pattern doesn't necessarily have to mean, oh, like they're in a perfect curve. It can say that, all right, there's something happening here that's not totally random, because for some reason, our predictions are really good in this range and we have really tiny residuals, and our predictions get much worse in this range where we get much larger residuals. So what does all of this mean? Like, how do we interpret this? So what do we notice? The points are randomly distributed above and below the line, but as x gets larger, the residuals start to increase. So what does that tell us? It basically tells us that the model seems to break down for larger values of x. So it does a really good job when our x is smaller, but it seems to break down as x gets larger, which suggests that maybe the relationship is changing. All right, maybe the model that we have for this range of values is really good. Maybe we need a different model for this range of values where it's falling apart. So the model seems to break down for larger values of x. All right, so again, it doesn't necessarily have to be, oh, the residuals are in a perfect curve. It could be something like this, where we're just noticing this general pattern here of, okay, they started small and they keep getting larger. All right. The ideal residual plot, there is no pattern. All right. It's random above and below, and it's random how big and how small they are. Basically, while looking at the residuals, you should be able to get no insight about how well your model is going to do. You shouldn't be able to say like, oh, my model is going to do really well in this section and really bad at this section. These points should be so randomly scattered that you're just like, yeah, sometimes the model gets it right, sometimes it gets it wrong, but there's no pattern in what it gets right versus what it gets wrong. If there's a pattern in what it gets right versus what it gets wrong, that suggests that there's some problem within the model and how you're setting up the equation, and whether or not it's truly a linear relationship. All right, so this is one way that we can evaluate our model. All right, we can take all of the residuals, which again is the actuals minus the predicted, plot those out, and then scan it for patterns. All right, and if we find any sort of pattern in this residual plot, it's an indication that we probably shouldn't be using a linear model. All right, now, this is just sort of a first step. Right? Another thing we can do to evaluate our model is how big are the errors? Like, how far off are our predictions on average? All right, so once we've established that, hey, yes, the linear model is fine, that doesn't tell us that it's a good model. We still need some measurement of how good we did. So one way to do that would be to look at the mean of the residuals. Right? The residuals are basically our error. So if we average those together, it would give us an idea of how much error we have. Now, there's a problem with this. All right? The problem is that the mean of the residuals will always be 0 plus or minus some rounding error. But for the most part, taking the average of the residuals isn't going to tell you anything, because the positives and the negatives are going to cancel each other out. And you're just going to be saying, oh, the average error is 0. Yeah, the average error isn't really 0. It's just that the positive errors canceled out the negative errors. So to measure average error, we use the standard deviation of the residuals. Now, if you remember, our definition for standard deviation is the average distance from the mean. All right. So if the mean of the residuals is always going to be 0, and the standard deviation is telling us the distance from 0, or the average distance from 0, then it's basically telling us the average error. All right. So instead of using the mean of the residuals, which is always going to be 0, we use the standard deviation of the residuals, which again is average distance from the mean. And since we already know the mean is 0, it's the average distance from 0. Remember, 0 represents no error, so it's giving us the average error. All right. So the value gives us the approximate size of a typical or average prediction error. And remember, prediction error is just another way of saying residual. All right. So how do we calculate the standard deviation of the residuals? Well, it's basically very similar to what we've done in the past. All right. It's going to be the square root of the sum of the residuals squared, all divided by n minus 2. So it's a little different because when we're just doing a regular standard deviation, it's n minus 1. When we're doing the standard deviation of the residuals, it's going to be n minus 2. So we could also write this as the square root of the sum of y minus y hat, which again is the same as just saying residuals, squared divided by n minus 2. All right. So some bad news. Your calculator will not directly give you this value. Right? So there is a process that we're going to have to go through to get this value. Now, the reality is most people don't do regressions on a graphing calculator. They do them on a computer. And any sort of computer software that you use will give you this value. And we're actually going to look at that a little later in the unit, like how to do some of this stuff on the computer versus your calculator. But if we're doing it on our calculator, there is a series of steps that we're going to have to go through. Right? Now, this box outlines those steps. I'm not going to read through this right now. I'm just going to do an example. But this is sort of your checklist of how you have to do it if you're doing it again on your own for a different problem. Okay? So let's actually do an example here so that you can see how this works. So this is the same data that we had last class when we were doing the regression equation by hand. All right. So again, I've already put it into the calculator. All right, there's all the data. It's in the calculator. All right, I'm going to run the regression on that. So let me just run the regression on that, L1, L2. All right, so our equation is y hat equals 0.01. We'll go 3 decimals on this one. 019x minus 0.015. Okay. So there's my equation. You can also write it the stats way. Again, it's up to you as long as you're writing it correctly. I don't care which format you use. It's the same equation regardless. Okay. So sketch a scatter plot. Again, we did this last class, but it is always a good idea to look at the scatter plot to make sure there's nothing weird going on with the data. There's no obvious, curved pattern that you want to be on the lookout for. So if we sketch it, all right, we get something that looks like this. All right, and to my eye, that looks pretty good. All right, so we're probably good here. All right, and then we'll just sketch this real quick. All right, so that's what we've kind of got going on there. Now, how do we make a residual plot? All right, so that's where this series of instructions is going to come into play. All right, so what we need to do is on our calculator, we're going to go back to stat edit. Now, here in L1, I have my X values. Here in L2, I have my Y values. What we're going to do in L3 is we're going to program the regression equation. All right. So to do that, we scroll over to L3. We go up so that our cursor is on L3. And then we're going to type in our equation. All right. So our equation is 0.019 times, now it's times X, but what we're going to have the calculator do is plug in every single X value. So we're going to say times L1. Right? And this will make it so that the calculator will go through and plug in every single L1 value. And then we can just subtract 0.015. All right? So by doing this, the calculator is going to go through and plug in every single value. All right? So now L3 has all of our predicted values. So let me finish writing what I was going to do here. And then L3 is going to have all of our predicted values. Then what we're going to do is we're going to use L4 to calculate all our residuals. All right, so L4 is going to be our residual calculation. And all that is actual minus predicted. All right. We know actual is in L2. We know the predicteds are in L3 because we just put them there. So again, it's actual minus predicted. And that's going to give us all of the residuals in L4. So again, I scroll over. I go up to L4. I say L2 minus L3, actual minus predicted. I hit enter, and then all of those will fill in. So now L4 has all of my predicted values. And then the last step is just to do a scatter plot on L1 and L4. All right, so again, second y equals, and then we're going to go to stat plot, and then you just have to make sure that you're using L1 for your x's and L4 for your y's, right? And then again, you can zoom 9 to get the stat zoom. Whoops. So if you're not getting a good picture, you can go to zoom 9 and get the stat view. And that right there is effectively our residual plot. Now, you might be saying to yourself, that just looks like a random scattering of points. Exactly, that's what we're hoping for when we do one of these. So again, the y is going to be the residuals. And then for us here, the x would be the beers consumed. And then if we're just kind of sketching this, we've got like a point here, we've got a point here, got one there, one there, one there, one there, one there. 1, 2, 3, 4. 1. All right, so something like that. Again, obviously that's not perfect, but it's close enough for our purposes. And it illustrates what we're hoping to see with one of these, that there's no distinct pattern. We've got some low residuals over here. We've got some high residuals on this end. Over on this end, we've got some low residuals. We've got some high residuals. They're randomly distributed above and below the 0 line, which again is no error. So all of this is what we're hoping to see with our residual plot. This says like, hey, the linear model that you're using is a fine choice. Like there's nothing here that suggests that the data is not linear. So you can continue on with what you have here. So again, this is how we can get a residual plot on our calculator. Unfortunately, there's not a quick and easy way. You do have to go through these steps of you program the regression equation into L3, all right? And then once you've programmed the regression equation into L3, you can calculate the residuals in L4, and then that's what you're actually graphing. All right, so again, this is kind of what you're programming into L3. This is what you're programming into L4 to get those values so that you can actually make your residual plot. Now, how do we go about getting the standard deviation? Right, because that's the other thing that we want to look at. We want to look at sort of the average error. Now, L4 now has all our residuals. So what we can do is we can go to stat, calc, one variable stats, and run them on L4. Now, it would be great if we could just read the standard deviation off of here. Unfortunately, we can't because this is using n-1 as part of its standard deviation calculation. And our formula here requires us to use n-2. All right, so how do we take what's here and use it to get our final result? Well, the good news is that what we have here, this sum of x squared 0.005259, all right, that right there is the top part of our equation here. All right, that is the sum of the squared residuals. Right, this is the sum of x squared. X is the residuals because we're using L4. So this is the top of our equation here. So if we continue on here, all right, on the calculator, this is the one that is showing the sum x squared. So we now know that this is the square root of 0.005259, 0.005259. At the top, the bottom is n-2. Right? Well, n is just our sample size. Our sample size was 15. So this basically becomes s equals the square root of 0.005259 divided by 15 minus 2, or effectively 13. So we can just do the rest of this on the calculator here, but we've got 0.005259 divided by 13, and then we can take the square root of that and get a standard deviation of 0.0201, we'll say, equals 0.0201. All right, so again, this value right here gives us the top of this equation, then we have to do the bottom part manually because the calculator is using n minus 1, and we need to use n minus 2. So this part we have to do by hand. If we read the standard deviation right off the calculator, you're going to get the wrong answer. All right, so again, there's a little bit that goes on here, on the calculator of programming it in, calculating your residuals, making the scatter plot, and then for the standard deviation, you can't just run one variable stats. You have to run one variable stats to get this. We get this from one var stats on L4, and then we have to do this part by hand. All right, so I'm just going to put the reminder here. Don't use the standard deviation from the calculator. Right, and the reason we can't do that is because it's using n minus 1, not n minus 2, which is what we need. All right. But this gives us our average prediction error. So on average, our predictions are going to be 0.02 off. Now, is 0.02 big? Is it small? That depends on the situation, all right? It might be that a 0.02 error is not a big deal, or it might be that it's a really big deal. Depending on like what you're actually dealing with in the setting that you're dealing with. For something like blood alcohol content, it might be a pretty big deal if you're 0.02 off on your blood alcohol content, especially if you're using that to make some sort of decisions in your everyday life. So again, really, your blood alcohol content should be 0 if you're going to be driving or doing anything like that. But depending on the activity or the setting or what's going on here, this might be a difference, might be a significant difference, or it might not be. That's up to you to kind of decide in the framework of which you're using your regression equation. All right, last tool here that we have to sort of measure the success of our regression equation, because that's really what we've been doing here, all right? The residual plot, the standard deviation of the residuals, all of that is a way of measuring our model, right? And measuring how good of a job it's doing. So the last thing that we're going to look at is the coefficient of determination, which is also sometimes called just the R-squared value. So this is the fraction of the variation in the values of y that is accounted for by the least squares regression. Right? You can almost kind of think of it as like the grade your model receives. Not exactly, but it gives you a sense for how well your model did making its predictions. Now, R-squared, why is it called R-squared? For our purposes, it is really only just the correlation squared. All right, so if you have the correlation and you square it, that is going to give you your R-squared value. Now, when you're dealing with regressions that have more than one variable, it's not that simple. But for our purposes, it is literally just the correlation squared. Now, what we're going to do down below is I'm going to kind of walk you through the longer, more involved sort of calculation and explanation of it. Just realize that when we're working in this class, it will always just be the correlation squared. So if you know the correlation, you can square it to get the R-squared value. If you know the r squared value, you can take the square root and get the correlation. You just then have to figure out whether it needs to be positive or negative. So again, it is just the correlation squared, but I am going to walk through kind of a more involved explanation of where it's coming from. All right, so let's take a look at the more involved explanation. So this is that r squared equals 1 minus SSE over SST. So what are those referring to? So SST is what you can think of as like the total variation, or you can think of it as residuals when using the average for all your predictions. So what does that mean? I give you an x value, and I don't try to use an equation to predict the y value. I just say, yeah, I think it's going to be whatever the average is for y. I give you a different x value. Again, I don't try to come up with a new prediction. I just say, yeah, I think it's whatever the average is for y. It means that we're seeing how bad of a job do you do if instead of actually trying to come up with an equation, you just always guess the average value. All right, so the way we would write this mathematically is it's the sum of y sub I, which are like your actual y's. So these would be your actual y, minus y bar, and then we're squaring it, for the same reason that we square the residuals in the regression equation. We don't want the positives to cancel each other out. And this is what we consider the total variation. All right, so again, instead of using an actual regression line, we're just guessing the average for everyone. So again, if we were to make like a little sketch here, and like here are your points, normally we use in a regression line and say, all right, how far off will we refer from the regression line? This is saying we've still got this same cloud of points, but instead of making a regression line, we're just always guessing the average. So this is the average. This is your regression. How far are we off if we just always guess the average as opposed to actually trying to find the right line? All right, so this is what we consider the total variation. All right, so SSE are the residuals when we use regression. All right, and this is like the sum of the squared errors. This is the total sum of the squared errors. But this is what we've been seeing, all right? This is just the square root or the sum of residuals squared, or basically the sum of y sub I minus y hat squared, all right? But it's the variation after regression. So when we do SSE, basically the sum of the squared residuals after regression, over SST, which is the total variation, or the residuals when we're doing it by the average, this is the percent of variation that remains unexplained. All right, so presumably this number is going to be smaller than this number because your error should be smaller after you've done regression, right? Whatever's left here, whatever error remains, is the percent that's unexplained. Like you didn't get rid of that error. So if we do 1 minus that, that's the amount that we've explained, all right? It's the amount of error that we've accounted for. It's the amount of error we've gotten rid of. Because again, if this is saying, oh, 20% is unexplained, then that means you explained 80% of it, all right? So when we do 1 minus SSE over SST, this is the amount explained, right? And that's what the R squared is really measuring. Now, again, for our purposes, it is just the correlation squared, but this is sort of the theory behind it. And this is sort of the theory behind it when you're doing more than one variable and you can't just square the correlation. We're basically seeing what's the total error when you just use the average. What's the error when you actually use your regression equation? And then kind of what's the ratio there? How much is remaining unexplained? How much error did we not, get rid of? And how much error, did we get rid of? Or how much error, did we explain? So in our setting here, all right, we had a correlation. Where is it? Where are we? Okay. Hold on, let me find it. I couldn't find it because it was on the calculator, not on my sheet. When we ran the regression, it told us the correlation was 0.904958419, and it gives you the R squared value as well. Now, again, these two numbers, if you square this number, you're going to end up with this number. So it's not like you have to go through this whole process to get the R squared value in this class. It's going to be given to you, and it is just this number squared. But if we went through this whole process, you would end up with this number, all right? With just two variables, that's the way that it works out. But again, if there were more variables, you've got to kind of go through this longer process here. So for us, it was 0.91, 0.90, so it's basically 0.81 or 0.82. So 82% of the variation in the data is accounted for by the least squares regression line of y on x. Or in our exact setting here, we can say we can explain 82% of the variation in BAC from drinks consumed. So basically what we're saying is, BAC goes up and down. We can explain 82% of that up and down just by looking at drinks consumed. What's the other 18%? Well, we don't necessarily know, but it could be things like body weight. It could be things like, what have you eaten that day? All sorts of other factors. So we can't explain all the up and down. We don't have all the information. But just by looking at this one factor, we can explain 82% of the up and down that happens in BAC. Can't explain all of it, but we can explain about 82% of it. All right, so again, this is just sort of another tool that we can use to sort of evaluate our model. All right, and again, as I was saying earlier, you can almost think of it as like a grade. So like, okay, we explained 82% of the variation. We didn't explain all of it, but 82% is pretty good for just looking at one variable, right? We also have standard deviation of residuals, which tells you your average prediction error. And again, depending on the setting, that may or may not be a good number. And then we have the residual plot to make sure that the linear model is appropriate for this data set. So again, all sorts of tools we can use to sort of evaluate whether or not our regression model is any good. Because as I said at the start, you can always calculate a regression model. Nothing stops you from running through the calculations and getting a model. It's up to you as the statistician to figure out if that model is any good or is really going to be useful to the people trying to use it. Okay? So I hope this was helpful. Have a good day, and I will see you when I see you.